In this section, we're going to be discussing rational functions and their graphs. We're first going to find the domains of rational functions. Then we're going to identify something called vertical asymptotes. We'll define them, and then we'll identify those. How do we find those? We'll identify horizontal asymptotes. We'll define them, and then we'll determine how we find those. We're going to use transformations just like we've done all semester long. We're going to use transformations to graph rational functions. Then we'll graph a rational function. We'll talk about slant asymptotes, and then we'll solve an applied problem. So what's the definition of a rational function? Earlier in chapter 3, we got the definition of what a polynomial function is. A polynomial function is a function such that no power on any of our variables can be a fraction or a negative number. They all have to be whole numbers. So a rational function is a ratio of polynomial functions. A rational function are quotients of polynomial functions. This means that the rational function can be expressed as f of x equals p of x over q of x, where p and q are both polynomial functions. And of course, q of x cannot equal 0. Division by 0 is undefined. So the domain of a rational function is the set of all real numbers except those x values that would make our denominator 0. So this is how we find the domain of rational functions. Let's look at some examples. All right, our first example, here we go. Our first example, we have f of x equals x squared minus 25 divided by x minus 5. This is a rational function because both the numerator and the denominator are polynomial functions. So with the way we find the domain is we set the denominator equal to 0 and see, are there any real numbers that would make that value 0. So we're going to set the denominator equal to 0. And then we'll solve the resulting equation. So we have x minus 5 equals 0. Let's add 5 to both sides. Then we get x is 5. So the domain of this rational function is every real number except x cannot equal 5. So the way we write this, we can write this in set builder notation. We say this is the set of all the real numbers x such that x cannot equal 5. In interval notation, if we looked at the graph, we would have a hole at the number 5, and x can be anything else, but it can't equal 5. So in interval notation, this would be the set from negative infinity to 5, union with from 5 to infinity. The domain of this thing has a jump at 5. It has to jump over that number. It can't equal 5. All right, let's look at another example. Here we have g of x equals x over x squared minus 25. So again, to determine the domain of this function, we set the denominator equal to 0. So we're going to set x squared minus 25 equal to 0. And we're going to solve the resulting quadratic equation. This is a quadratic equation because of that 2 in our exponent right there. So you could solve this 3 different ways. You could certainly factor it. This is the difference of 2 squares. It's one of our special products. Or you could use the square root property, just what I'm going to use. Or you could use the quadratic formula. We know that the quadratic formula will solve any quadratic equation. So I'm just going to add 25 to both sides. And I get x squared equals 25. Then I'm going to take the square root of both sides, and when I do that, I have to put that plus or minus on the right-hand side of the equation. So the square root of x squared is x, plus or minus the square root of 25. The square root of 25 is 5. All right, so our domain excludes -5 and 5 because those two numbers would make my denominator equal to 0. So in set builder notation, we'd say it's the set of all the x's, but x cannot equal -5, and it cannot equal 5. So there would be set builder notation. Now, interval notation, we're going to have to union 3 different intervals because now we have to exclude -5, and we also have to exclude +5. So the graph would look like this. At -5, we'd have a hole. At +5, we'd have a hole, but we could have everything else. We just can't have those two numbers. So we'd have from -infinity to -5, from -5 to +5, sorry about that, and we'd have from 5 to infinity. All right, so let's look at one more example. We have h of x equals x plus 5 over x squared plus 25. And we did do an example just like this from chapter 2. This is the case where if I set the denominator equal to 0, which is how I would find the domain of this function, we probably quickly see that there is no real number that I can replace x with and add 25 and get 0. It doesn't exist. Because anytime I square a real number, I'm going to get a positive number. And when I add a positive number to 25, I'm not going to get 0. Now I could go ahead and solve this. I'm going to subtract 25 from both sides. I'm going to use the square root property. I'm going to take the square root of both sides. Make sure I put that plus or minus in front of my square root. And the square root of -25 is not a real number. It's an imaginary number. So when I take the square root, I get plus or minus 5i. The square root of -25 is 5i. That's not a real number. And remember, in the domain, we're always talking about a set of real numbers when we're talking about the domain of a function. Functions deal with real number inputs. So there are no real numbers that I can input for x and get 0 for my denominator, which we already discussed by just looking at it. You could have determined that. So the domain of this rational function is the set of all real numbers. There is no restriction on my value x, my input. So it's from -infinity to +infinity. All right. Now let's discuss vertical asymptotes. The line x equals a, and remember every vertical line has an equation x equals a constant. The line x equals a is a vertical asymptote of the graph of a function f if f of x increases without bound as x approaches a. So let's look at this first graph here. In this first graph, we can see that as x approaches this vertical line from the positive direction, that's what this means right here. X approaches a from the positive direction, the value of my function increases without bound. As x comes from the positive direction and it approaches that line, the graph just takes off to positive infinity. When we look at the second graph, the graph on the right, now we're approaching that vertical line from the negative direction. That's what this means right here. As x approaches from approaches A from the negative direction, the same thing happens. Y increases without bound as X approaches that vertical line. And that is the definition of a vertical asymptote. As the function approaches that vertical line, Y just takes off and goes to positive infinity. Vertical asymptotes are vertical lines that my graph cannot cross or my graph cannot touch. My graph approaches that line and increases without bound, but never crosses it and never touches it. Now it can also decrease without bound, which is the second slide here. The graph on the left shows a function approaching a vertical asymptote from the positive direction and decreasing without bound. So as the graph of my function approaches this vertical line from the positive direction, Y decreases without bound. So what this says down here is as X approaches this value A from the positive direction, Y goes to negative infinity. It decreases without bound. The second graph, the graph on the right, shows the same thing, but now we're approaching that vertical line X equals A from the negative X direction. And as X approaches that line from the negative direction, the value of my function decreases without bound. So as A comes toward that vertical line, as X comes toward that vertical line, Y goes to negative infinity. It completely decreases without bound. So that's what vertical asymptotes are. Again, you can't cross a vertical asymptote. You can't touch a vertical asymptote. The graph comes along and skims that vertical line, but it never crosses it and it never touches it. It can increase without bound at a vertical asymptote, or it can decrease without bound at a vertical asymptote. All right, how do you find them? So to locate a vertical asymptote, if you have a function f of x equals p of x over q of x, it's a rational function in which p of x and q of x have no common factors. So if they do have common factors, you're going to have to cancel those out. And A is a zero of P of X, of Q of X. A is a zero of the denominator. Then X equals A is a vertical asymptote of the graph of F. So the way you find vertical asymptotes is you factor the numerator and denominator completely. You cancel any common factors in the numerator and denominator. Then you set the denominator equal to 0. If there are values that would make my denominator equal to 0, then that would be a vertical asymptote. Let's look at some examples. Find the vertical asymptotes, if any, of the graph of the rational function f of x equals x divided by x squared minus 1. Now I can factor that denominator, and I need to do so. That is one of our special products. It is the difference of two squares. X squared is a perfect square, 1 is a perfect square, and we're subtracting them. So it's the difference of two squares. And to factor the difference of two squares, that factors to the sum times the difference. So this factors to x over the square root of x squared is x, plus the square root of 1, which is 1, times the square root of x squared is x, minus the square root of 1, which is 1. So now I have the denominator completely factored. Now, can I cancel any factors from the numerator and the denominator? And the answer is no. There's no common factors in the numerator and denominator. So to find the vertical asymptotes, I set that denominator equal to 0. If I could cancel a common factor, I would, but I can't. So I'm just going to set that denominator equal to 0. Since I have it factored, I might as well set it equal to 0 in factored form. Using the zero product principle, I'm going to set each factor equal to 0. So I'm going to subtract 1 here. I'm going to add 1 here. And those are my vertical asymptotes. I have a vertical asymptote at -1, and I have a vertical asymptote at +1. And you will note that those are restrictions on the domain of my function. I can't have x equal to -1 or x equal to +1. So as my function approaches those two vertical lines, it's going to increase or decrease without bound. And there is the graph of this function, and sure enough, you can see that that's exactly what it does. As x approaches from the negative direction, as it approaches the line x equals -1, it decreases without bound. In between those two vertical asymptotes, it both increases without bound as it approaches that line x equals -1 from the positive direction, and it decreases without bound as it approaches the vertical asymptote x equals 1 from the negative direction. And then as it approaches from the approaches that vertical asymptote x equals 1 from the positive direction, it increases without bound. So that's what vertical asymptotes describe. They describe what happens to the value of the function, the y value, as it approaches this line. All right, how about this one? This one, there is not going to be any vertical asymptote because, number one, I cannot factor that denominator over real numbers. The sum of two squares does not factor over real numbers. It factors over imaginary numbers. So there are no real numbers for which I can substitute in for x, square it, add 1, and get 0. So because of that, there are no vertical asymptotes. And you can see from the graph that there isn't. That as x goes to positive infinity, there is no vertical line for which y increases without bound, and the same as in the negative direction. So there are no vertical asymptotes. All right, let's look at another example. We have f of x equals x minus 2 over x squared minus 4. Now remember, to find vertical asymptotes, you need to cancel any common factors in the numerator and denominator first. So I'm going to go ahead and factor my denominator, and it does factor. It's the difference of two squares. X squared is a perfect square, 4 is a perfect square, so it will factor to a sum times a difference. All right, so I'm going to go ahead and factor that. So it factors the square root of x squared is x. The square root of 4 is 2. So it's going to factor to x plus 2, x minus 2. And so you can see that we have a common factor of x minus 2, so I can cancel that. When I cancel that common factor in the numerator, then I get 1 in my numerator. So I get f of x equals 1 over x plus 2. So now I'm going to set that denominator equal to 0, and that is going to give me my vertical asymptote. So this function has a vertical asymptote at x equals -2. Okay, but x cannot equal 2. Would you agree with that? Because if I replace x with the number 2, 2 squared is 4, 4 minus 4 is 0. So x can't be positive 2. So that is a restriction on my domain. So I have an asymptote at -2, but I have a hole in my graph at positive 2 because I cannot let x equals positive 2. That would cause division by 0, and that's undefined. So the graph of this thing has a vertical asymptote at -2, which we determined, but it has a hole right here at +2, and that's kind of hard to see on this slide, but there is a hole there. That is a restriction on the domain. So vertical asymptote at -2, which you can see, let me draw that in with a dashed line. There is my vertical asymptote. As the graph of my function approaches from the negative direction, the value of this function decreases without bound. As we approach from the positive direction, this function increases without bound, but there's a hole at 2. So it cannot equal 2 because of the restriction on the domain. All right, let's talk about horizontal asymptotes. The line y equals b, and remember that if it is a horizontal line, the equation of a horizontal line is y equals a constant. The line y equals b is a horizontal asymptote of the graph of f, the function f, if f of x approaches this value b as x increases or decreases without bound. So what this means is this is a value that y approaches as x goes to infinity or negative infinity. So it's just a value. And yes, our graph can cross, it can touch horizontal asymptotes. So look at this first graph here. As x approaches infinity, so as it goes off to the right forever, my graph is approaching a particular value. So y is approaching a particular value. That's a horizontal asymptote. In this graph, we have the same thing going on. It's just approaching from the top and going down. As x goes to the right to infinity, my graph's value, the y value, is approaching this number b. And this last graph shows that your graph can cross a horizontal asymptote. It's not like a vertical asymptote that is the brick wall. Your graph can cross that horizontal asymptote. But as x goes to infinity, so it goes to forever to the right, the value, the y value of my function approaches this number b. All right, how do we find them? All right, so we have some rules that we use to find horizontal asymptotes. Let f be the rational function given by f of x equals a polynomial function of degree n in the numerator and a polynomial function of degree m in the denominator. The degree of the numerator is n. The degree of the denominator is m. If the numerator's degree is less than the denominator's degree, then the x-axis, or y equals 0, is a horizontal asymptote. If the degree of the numerator and the degree of the denominator are equal, then there is a horizontal asymptote, and it's found by taking a ratio of the leading coefficient of the numerator divided by the leading coefficient of the denominator. So you just take that quick ratio of the first constant divided by the bottom constant, the first constant in the denominator. Let me say that correctly. And if the numerator's degree is larger than the denominator's degree, then there is no horizontal asymptote. All right, let's do a couple of examples. Find the horizontal asymptote if any of the graph of the rational function f of x equals 9x squared divided by 3x squared plus 1. So let's first look at the numerator. The numerator is 9x squared. The degree of this numerator, looks like my slide did not. Looks like we have a delay in the sharing here, so let me unshare real quick and reshare so that we can speed this up. Technical difficulties. There we go. Yeah, I think I'm good. All right. Again, the numerator of this function is 9x squared. That is a polynomial function, and its degree is 2. Degree is that exponent right there. And we call that n. All right, now let's look at our denominator. Our denominator is 3x squared plus 1. The degree of that denominator, which we call m, is also 2. And from our rules for finding horizontal asymptotes, if the degree of the numerator is equal to the degree of the denominator, then the horizontal asymptote can be found by taking a ratio of the leading coefficients. So it's y equals a sub n over b sub n. So in our case, our leading coefficient of our numerator is 9. The leading coefficient of our denominator is 3. So our horizontal asymptote is the number y equals 3. So as x increases without bound, then the value of our function approaches the number 3. And I'm pretty sure that I wrote right over the top of the graph, but you can see from the graph that that's exactly what's happening. As x is increasing without bound, the value of my function approaches the number 3. Also, as x decreases without bound, so as x goes to negative infinity, the value of this function also approaches the number 3. So if the degree of the numerator equals the degree of the denominator, you can find the horizontal asymptote by taking a ratio of the leading coefficient of the numerator over the leading coefficient of the denominator. All right, let's find the horizontal asymptote of this rational function. So let's first look at the numerator. The numerator is 9x. The degree, which we call n, is 1 because that exponent is that understood 1. Now let's look at our denominator. Our denominator is 3x squared plus 1. The degree of our denominator, which we call m, is 2 because that largest exponent there is the number 2. So if the degree of my denominator is larger than the degree of my numerator, which it is, 2 is larger than the number 1, then we have a horizontal asymptote that is the x-axis, or y equals 0. So as this function increases without bound, the y value approaches 0. The value of the function approaches 0. And we can see from the graph that that is true. As x increases without bound or decreases without bound, the value of my function, the y value, is approaching 0. Our last example, h of x equals 9x to the third over 3x squared plus 1. Again, let's look at the numerator of our rational function, that is 9x to the third. The degree, which we call n, is 3 because that exponent on that x in that numerator is the number 3. Now let's look at our denominator, which is 3x squared plus 1. The degree of our denominator, which we call m, is 2. And if the degree of the numerator is larger than the degree of the denominator, which it is, 3 is bigger than 2, then there is no horizontal asymptote. And we can see from the graph that that is true. As a matter of fact, as x increases without bound, so does y. Y goes to positive infinity. And as x decreases without bound, so does y. Y decreases without bound. So y goes to negative infinity. All right, so our two basic reciprocal functions are f of x equals 1 over x and f of x equals 1 over x squared. Let's first look at 1 over x. 1 over x is an odd function, and it's odd because if I replace x with negative x, I get negative f of x, and that is our definition of an odd function. So it has symmetry about the origin. It goes through the point 1, 1. It also goes through the point negative 1, negative 1. It has a vertical asymptote at 0 because x cannot equal 0. So we're going to have a vertical asymptote there. And it has a horizontal asymptote at y equals 0 because the numerator's degree is 0 and the denominator's degree is 1. So the numerator's degree is less than the denominator's degree. Our second function, f of x equals 1 over x squared, is an even function. This is even because if I replace x with negative x, I get exactly the same function I started with. I get 1 over x squared. So it's even, so there's symmetry with respect to the y-axis. So the graph of this function goes through 1, 1, but it goes through negative 1, 1 also. It has a horizontal asymptote at y equals 0 because the numerator degree is less than the denominator's degree. And it has a vertical asymptote at x equals 0 because x cannot equal 0. We can't let x equal 0 in that denominator. So it has a vertical asymptote at x equals 0. Excuse me. Yes, x equals 0. All right, so let's graph if my slide will catch up. There's a little delay in my slide here. So let me just let it. We have technical difficulties in recording a video. Now let me stop sharing and reshare again. See if that works. There we go. All right, here we go. So let's use the graph of one of our standard reciprocal functions, 1 over x, to graph g of x equals 1 over x plus 1 minus 1. So just looking at the original graph, f of x equals 1 over x, we know that it goes to the point 1, 1. It goes to the point negative 1, negative 1. We got a typo right there. That is a typo. And there's a horizontal asymptote at y equals 0 and a vertical asymptote at x equals 0. Now, from our transformations from chapter 2, we do know that we have a couple of transformations going on here. Remember that if you add a value to x, that's a horizontal translation, and it's a translation to the left. If you add a constant, you translate to the left. If we subtract a number from our function, that is a translation vertically, and it's a translation down. If we add to our function, it's a translation up. If we subtract, it's a translation down. If we add to our x, it's a translation to the left. If we subtract from the x, that's a translation to the right. So this is going to take that standard reciprocal function, 1 over x, and move it 2 units to the left and 1 unit down. Okay, so let's first move it to the left, and it moves everything, including the asymptotes. So every horizontal point gets moved 2 units to the left. So the vertical asymptote, which was at x equals 0, gets moved to x equals negative 2. And I think you could see from that function that x cannot equal negative 2. So that would be a vertical asymptote in this rational function. The horizontal asymptote we haven't moved yet because we haven't done the vertical translation. But let's do that now. We're going to move this whole function down 1 unit. And when we move it down 1 unit, the horizontal asymptote also gets moved. So not only have we moved the vertical asymptote 2 units to the left, we've moved the horizontal asymptote 1 unit down. So now the horizontal asymptote is y equals -1. All right, so now let's use a little strategy to graph these. Now I strongly encourage you to use your graphing calculator to graph these also. Now to graph these on your graphing calculator, I would use my fraction button. And as you recall, let me write this up here. To get to your fraction button, you hit the alpha key and y equals. So while you're in your y equals, hit the alpha key, y equals again. That'll bring up your fraction menu. Number 1 is your fraction. Put that into your y equals, and then you can type the numerator and denominator separately. You can also do this by using parentheses. Type your numerator in, and then use your division symbol and type in your denominator. Just be sure you put your numerator and denominator both in parentheses if you do it that way. Okay, the following strategy can be used to graph f of x equals p of x over q of x, where p and q are polynomial functions with no common factors. Number 1, determine whether the graph of this function has symmetry. So how do we determine symmetry? To determine symmetry, we replace x with -x. If we get exactly the same function we started with, then there's some symmetry about the y-axis. If we get exactly the opposite of what we started with, then there's symmetry about the origin. Next, find the y-intercept, if there is one, by evaluating the function at 0, and there may not be a y-intercept. Next, find the x-intercepts by setting the numerator equal to 0. Denominator cannot equal 0, but the numerator can, because you can have 0 in the numerator of a fraction. You cannot have 0 in the denominator of a fraction. So to find the x-intercepts, you set the numerator equal to 0. If there are any values for x that would make your numerator equal to 0, those are your x-intercepts. Step 4. Got a delay in the slides again. You know, this isn't perfect, this way I'm recording these videos, but it seems to be, all in all, the best way for me to do it. I'm using Zoom meeting and I'm recording the meeting, and so sometimes there's a delay in my changing of slides. All right, so where were we? Step 4. Find any vertical asymptotes by solving the equation q of x equal to 0. Again, make sure there's no common factors. If there are, you're going to cancel those out to find the vertical asymptotes. Find any horizontal asymptote. If there is one, use those rules that we got earlier to determine the horizontal asymptote, if there is one. Plot at least one point between and beyond each x-intercept and the vertical asymptote, and use the information obtained previously to graph the function between and beyond the vertical asymptotes. So you are going to have to answer a certain number of questions in MyMathLab regarding the graph of your function, and then you're going to have to determine the graph. Again, you're going to have a multiple choice and you pick the correct graph. So you can let your calculator help you determine the correct graph, but you do have to answer these various questions before you get to the graph. All right, so let's graph f of x equals 3x minus 1 over x minus 2. So the first thing we're going to determine, is there any symmetry with respect to the y-axis or the origin? So we're going to evaluate this function at -x. So I'm going to replace x with negative x in the numerator and the denominator. All right, so what do I get here? I get negative 3x minus 3 over negative x minus 2. Now, I think I'm going to go ahead and factor out a negative from the numerator and the denominator. That'll help me determine. And a negative divided by negative is going to be a positive. So when I replace x with negative x, I get 3x plus 3 over x plus 2. Okay, that is not the same function I started with. It is also not exactly the opposite of the function I started with. For it to be exactly the opposite, I would have to have negative 3x plus 3 in the numerator. It's not exactly the opposite. So there is no symmetry for this function. All right, so the next thing we're going to do is we're going to find the y-intercept. And we're going to find the y-intercept by evaluating the function at x equals 0. So my function is f of x equals 3x minus 3 over x minus 2. So I'm going to evaluate this function at 0. So I'm going to replace the x with 0. So I get f of 0 equals 0 minus 3 over 0 minus 2, which is negative 3 over negative 2, which is 3/2. So I do have a y-intercept, and it occurs at 1.5. All right, now we're going to find the x-intercepts. And to find the x-intercepts, I'm going to set the numerator equal to 0. Again, the denominator cannot equal 0. So we set the numerator equal to 0 to determine any x-intercepts. So 3x minus 3 equals 0. I'm going to add 3 to both sides. Divide by 3, and I get x is 1. So it does have an x-intercept at the number 1. All right, so what's next in our graphing step-by-step procedure? We're going to determine any vertical asymptotes. So again, my function was f of x equals 3x minus 3 over x minus 2. And I do need to factor that numerator just to make sure I can't cancel anything. I'm going to factor out a 3. And there is nothing I can cancel there. X minus 1 and x minus 2 are not common factors. So there's nothing I can cancel. So I'm going to set the denominator equal to 0 and solve the resulting equation. So there is a vertical asymptote at x equals 2. So next we're going to find the horizontal asymptote. So we're going to look at the degree of the numerator and the degree of the denominator. The degree of the numerator and the degree of the denominator is 1. So n is 1, as is m. m is 1. And since the numerator degree equals the denominator degree, we can find the horizontal asymptote by taking a ratio of the leading coefficients. So it would be y equals 3. The leading coefficient in the numerator is 3 over 1. There's an understood 1 in front of that x. So our horizontal asymptote is y equals 3. All right, so now let's put everything that we've learned so far in our graph. So we're going to plot these points. The x-intercept is 1, so we plotted that. The y-intercept is 0, 1.5, so we plotted that. We have the vertical asymptote plotted at x equals 2. All right, so we would probably want to pick a few x's beyond these points. So we would evaluate maybe x equals -1, x equals 1/2, And then to the right of that asymptote, maybe x equals 5/2 and x equals 3. Okay, so I'm going to evaluate the function at each of these x's that I picked. So if I replace x with -1 in my function, the value of my function would be 2. So there's a point that's on the graph on my function, -1, 2. I'd replace x with 1/2 and evaluate my function. And you can do this on your calculator. Let your calculator evaluate this for you. When x is 1/2, y is 1. When x is 3/2, y is -3. When x is 5/2, y is 9. When x is 3, y is 6. And I can plot those points. Okay, so let's do that. We had a vertical asymptote at x equals 2. I'm going to draw that in using a dashed line. And in MyMathLab, you need to be sure that you use your dashed line when you graph your asymptotes. Don't use a solid line or it's going to count it incorrect. We had a horizontal asymptote at what, 3? So I'm going to go ahead and draw that in. So here's my vertical asymptote at x equals 2, my horizontal asymptote at y equals 3. And we had a y-intercept at 1.5, so I'm going to plot that. We had an x-intercept at 1, so I'm going to plot that. I'm going to plot those points. We had -1, 2. I'm going to plot that right there. We had 1/2, 1. 1/2, 1 was about right there. We had 3/2, -3. 3/2, -3 is right there. So I can get a pretty good idea of what it looks like below that asymptote and to the left of it by just graphing those points. It does look like it's doing something like this. So again, as it approaches that horizontal asymptote, as x is going to -infinity, it is approaching the value of that horizontal asymptote. So as x goes to -infinity, y is approaching the number 3. But as it approaches that vertical asymptote from the negative direction, y decreases without bound. All right, let's plot a few more points. We had 5/2 and 9, so 2.5 and 9, and I don't have 9 on my graph. It's up here somewhere. And we have what, 3, 6, 3, 6. So it looks like what it's doing on this side is doing something like this. All right, so again, as it's approaching that vertical asymptote from the positive direction, y is going to increase without bound. And as x goes to infinity, as x increases without bound, the value for y is going to approach the number 3. All right, slant asymptotes. The graph, so what do we mean by slant? I guess we should say that first. If the slope is not 0, horizontal, or the slope is not undefined, then if the slope is not 0 or undefined, then the slope has a value that's not 0 or undefined. And so that makes it a slant asymptote. The graph of a rational function has a slant asymptote if the degree of the numerator is more than the degree of the denominator. In general, if f of x equals p of x over q of x, p and q have no common factors, and the degree of p is 1 greater than the degree of q, you can find the slant asymptote by dividing the numerator by the denominator. So you can use long division, or you can use synthetic division. And I'm pretty sure all the homework that's assigned, you can use synthetic division. All right, so let's find the slant asymptote of this function. And again, I'm having slide delay here. So let me unshare, reshare, there we go. All right, so let's find the slant asymptote. So this thing's going to have a slant asymptote if the numerator's degree is 1 more than the denominator's degree. And my numerator's degree, n, is equal to 2. It's a second degree polynomial function in that numerator. And the denominator's degree is 1. So the numerator's degree is 1 more than the denominator's degree. Now I probably need to factor this thing to make sure there are no common factors. And I'm not sure that that's factorable. I'm not sure that numerator is factorable. So we're good to go there. All right, so how do I determine what the slant asymptote is? I'm just going to use synthetic division. And I can use synthetic division because my denominator is in the form x minus a constant. So I can use synthetic division if it's a first degree divisor in the form x, 1x, minus or plus a number. So I'm going to set up my synthetic division. I'm going to divide by 2. 2 minus 5, 7. And then I'm going to bring the 2 straight down. 2 times 2 is 4. Negative 5 plus 4 is negative 1. Negative 1 times 2 is negative 2. 5. All right, so I don't really care about the remainder. I don't care. I'm concerned only with the quotient. The quotient is the equation of my slant asymptote. So I have a 2, which is going to give me 2x. The minus 1 is my constant. Y equals, that is my slant asymptote. So again, I'm not really concerned about the remainder at all. All right, so how do I find a slant asymptote? If the numerator's degree is 1 more than the denominator's degree, I can find the slant asymptote by dividing the numerator by the denominator. If the denominator, the divisor, is a first degree polynomial function in the form x minus or plus a constant, then I can use synthetic division. If not, then I would use long division. All right, and there is the graph of my slant asymptote in my function. All right, let's do an application. A company is planning to manufacture wheelchairs that are light, fast, and beautiful. The fixed monthly cost will be $500,000, and it will cost $400 per chair to produce these. Write the cost function C of producing X wheelchairs. Okay, so we've done this several times this semester, written a cost function. And a cost function is the fixed cost of creating our item plus the variable cost. So our cost is going to be, we have a fixed cost. No matter how many chairs we manufacture, if we manufacture none or you manufacture 1,000, we have a fixed cost of $500,000. That's to rent the building, keep the lights on, pay our employees, whatever we need to do, that's our fixed cost. But each wheelchair costs money to produce. Materials, again, maybe to pay our employees, someone to put these things together, whatever it costs, each one of those costs us money to manufacture. Each one of them costs us $400 to manufacture. So our variable cost is going to be 400 times the number of these things that we make, which would be 400x. So our cost function is 500,000 plus 400x. All right. What's the average cost function? And you see that we got C with a bar over the top of that. That means average. So the average cost function would be our cost. How do you find the average? To find the average, you take the total number you have and divide it by the number of things you have. So in this case, the total cost, 500,000 plus 400x, divided by the number of wheelchairs that we manufacture would be our average cost. So we have a rational function. The average cost is 500,000 plus 400x divided by the total number of wheelchairs we manufacture, x. All right, let's see what happens when we evaluate this function at various values of x. All right, and I'm going to let you do this on your calculator. So we would take our function c of x, c bar of x equals 500,000 plus 400x divided by x, and we'd evaluate for each of these values. When I evaluate it at 1,000, I get 900. When I evaluate it at 10,000, I get 450. When I evaluate it at 100,000, I get 405. So what does this mean? This means if I make 1,000 wheelchairs, the average cost of producing 1,000 wheelchairs would be $900 a piece. Fixed cost plus variable cost, the average cost would be 900. If I make 10,000, my average cost is going to be 450. If I make 100,000, my average cost is going to be 405. Can you see what's happening here? The average cost is decreasing as the number of these things increase. Wait a minute. If I have a rational function as x increases without bound, and I approach a value, that's a horizontal asymptote. So let's look at this function and let's look at its horizontal asymptote. Now, this function, the numerator is 500,000 plus 400x. So the degree of that numerator is 1, because we have an exponent of 1 on our x. The denominator's degree is also 1. And if the numerator's degree equals the denominator's degree, then you can find the horizontal asymptote by taking a ratio of the leading coefficients. So our leading coefficient here is 400 because 400 is what we're multiplying times our x. And our leading coefficient here is 1. So our horizontal asymptote is y equals 400. So what's happening here? If we were to graph this, which you could, you'd have to really change the window on your calculator. But if we were to graph this, we would see that as x increases without bound, the value of our function approaches 400. So the average cost to manufacture wheelchairs would approach $400 a piece. Now what happens here is that the 500,000 becomes negligible. And you can kind of see that as x goes towards infinity, this poor little 500 becomes a negligible amount. So the more wheelchairs we manufacture, the lower our average cost becomes. So our horizontal asymptote for this function is y equals 400. What does this mean? The cost per wheelchair approaches $400 as more wheelchairs are manufactured. All right, that ends section 3.5. Hope you found this helpful, and hopefully you'll let me know if you have any questions. Bye-bye.